In the previous lecture, we discussed Maxwell's equations. The Maxwell's equations are the fundamental quantities that are always true in classical electromagnetics. Whenever the classical rules apply and we aren't dealing on quantum scales, we can always apply Maxwell's equations. Part of electromagnetics is simplifying Maxwell's equations or making particular assumptions that are true under particular scenarios that allow us to get a set of different equations that we can solve. And the first one of these, one of the important ones, is the wave equation. Today we're going to talk about how to go from Maxwell's equations to the wave equation. And then in the next lecture, in lecture 5a, we're going to talk specifically about what happens with time harmonic fields, and we're going to get to the Helmholtz equation. The two learning objectives for this lecture, first of all, is to understand how the wave equation relates to Maxwell's equations. So we are actually, in most cases, not going to ever directly solve Maxwell's equations. Instead, we're going to solve secondary equations that we get from combining some of the Maxwell's equations. And you need to understand where this derivation comes from. You don't need to be able to reproduce it. You don't need to memorize it. You don't need to be able to show it. But you need to comprehend it. And you should also be able to verify that a given solution satisfies the wave equation. And at the end of the lecture, we're going to talk about some of the classes of solutions to the wave equation. So at the end of today's lecture, you should know several of these solutions, but throughout the course of the rest of ZEIT3220, we're going to talk very much about some particular classes of solutions, namely plane waves, which you should know extremely well, waves propagating on transmission lines. You've learned a little bit about voltage waves. Well, we're going to talk about the electromagnetic field waves, waves propagating in waveguides. So some of the things we're going to talk about today, I really just want you to see them, but a few of these we're going to bring back and we're going to talk about extensively throughout the rest of the term. So when I took this class, I realized something, and that is that really all we have to do is be able to solve these four equations. So I need to just solve Maxwell's equations. Just a set of differential equations, apply some boundary conditions. It turns out it's not that easy. And one of the things that students struggle with is that they struggle with the fact that there's many different ways to solve Maxwell's equations, many different types of boundary conditions, many different forms of solutions. And they get consumed with all these different recipes without remembering back down to the basics that all we need to do is be able to solve these four equations, which were always true. In order to be able to solve them, we need to make some additional statements. And so we're going to work with a particular set of constitutive relationships. These are not always true, but these are true for the types of materials we're interested in. These are simple, linear, isotropic, and homogeneous. One being that the displacement vector or the electric flux density D equals epsilon E. Right? So the D field is parallel to the electric field and linearly proportional to its strength. And the B field is equal to mu H, and where epsilon equals epsilon naught times epsilon sub r. Same thing for mu. The last one is the fact that the current density in amps per square meter is equal to the conductivity times the applied electric field. And again, this doesn't have to be true, but it is true in a wide class of materials that we're going to be interested in. So what's so hard about this? Well, there's a lot of things that are hard about this. First of all, we have a set of four coupled partial differential equations. Right? You guys probably are reasonably comfortable solving a few different types of ordinary differential equations. These are coupled partial differential equations. The unknowns, the quantities that we're interested in solving for, D, B, E, H, current, are all vectors. Right? Not just scalars, they're vectors. We have three spatial variables. So each of these nice upside down triangles, the del operator or the nabla operator, each of these corresponds to a partial derivative with respect to x, y, and z and carries a vector component with it. And in addition, we have the time derivative we have to worry about as well. And we need to deal with the boundary conditions. And we talked in the last lecture about boundary conditions and what that means. We need to enforce those boundary conditions. So we can come up with general classes to solve these partial differential equations, but those classes need to be made to satisfy the boundary conditions at the edges of our problem. So maybe electromagnetics isn't quite so simple after all. So we're going to consider one particular simple case. And we're going to consider the case, well, it's not too simple, but it's an important case that's not too complicated. And that is a source-free region of space, which means that there's no charge density, no current density. Right? Rho and J are both equal to 0. That's what we mean by source free. And we're going to assume that the permittivity and the permeability are constant. So I've got an epsilon and I've got a mu. Start with my Maxwell's equations. Right? So my Faraday's law is that the curl of the electric field is equal to the negative rate of change of the magnetic flux density. And I can take the curl of both sides of that expression. Right? So take the curl of both sides, and on the left I have del cross E, because remember, del cross E itself is a vector, right? So this quantity here is itself a vector, and so I can take the curl again. Under most circumstances, at least most of the ones that we care about, I am able to interchange these spatial derivatives with this temporal derivative, and so I'm going to swap the minus d by dt with the del cross, and I'm also going to substitute in my constitutive relationship v equals mu h. And so I end up with this expression here, and since we've made the assumption that the permittivity and permeability are constant in both space and time, I can pull that mu out front. Right? So the mu really belongs in there, but it comes out. There are many materials for which mu is not constant in space, many materials for which mu may not be constant in time. So it's not always the case that I can do that. But for the types of problems we're going to be interested in, we can. Well, I've got this time derivative of del cross h, but I had another Maxwell's equation, and that Maxwell's equation was that the curl of h was equal to j plus d dt. And here I've substituted in for d, I've substituted in epsilon e. Right? And we can make a similar set of arguments here. We are working in a source-free region of space, so the current density is equal to 0. And the dielectric constant, the relative permittivity can factor out. And I've also now substituted in a vector identity. You don't know this. I'm just telling you it's true. You can actually show it if you do all the derivatives. Most electromagnetics textbooks will include this in a lookup table. Some advanced math books will show you how to get it. And it's del cross E. I can write that as the gradient of the divergence of E minus del squared of E. And del squared is a complicated vector operator, but you can think of it as the second derivative, right? Two derivatives with respect to x, two derivatives with respect to y, two derivatives with respect to z. And we're going to see under certain circumstances that's exactly what it becomes. Right? So now I can start combining things. Del dot E, well, del dot E is equal to rho over epsilon, but we said that rho is equal to 0, so that quantity goes to 0. And on the right-hand side, I have the time derivative of the time derivative, so that gives me the second derivative. And I can pull everything over to one side, and the result is the wave equation. And what the wave equation says is I take two derivatives in space of my quantity minus some constant times two derivatives in time of that same quantity is equal to, and that's equal to 0. So this equation here is the wave equation, or the source-free wave equation in simple materials. What do solutions to this wave equation look like? Well, the one that we're going to spend the next couple of weeks talking about are plane waves. Right? So I can have a series of planar surfaces, and I can have phase fronts that are constant on these constant planes propagating from, say, left to right. Right? So this could be my plane wave solutions. Right? Or perhaps I might have a line source of current. So I've got a line of current here that's oscillating, and that line of current is going to give rise to cylindrical wavefronts that are propagating away from the source. Right? So radially outward propagation, depending upon where I'm sitting. That's the direction that the wavefronts are going to propagate. Or if I have a point source, perhaps I have spherical waves. So maybe what I've got in here is a small electromagnetic dipole that's oscillating, and it's giving rise to fields that come out like this and propagate out in this direction. And here are my spherical phase fronts. And so these are all free space solutions. There are other types of free space solutions, but these are the three that we're going to deal with most of the time. And in point of fact, most of the time we deal with plane waves or spherical waves. I can also have combined solutions or guided solutions, and for example, a coaxial line. I'm in a coaxial line. We have an inner conductor and an outer conductor, and I'm going to apply a time-varying potential across that conductor, and I'm going to allow that, I'm going to connect this up to a voltage source that I'm going to allow to oscillate in time. So there's my coaxial line. When I apply that potential difference, I end up setting up electric fields that go from positive charge to negative charge, and magnetic fields that rotate around the center conductor. Okay. Now, in order to demonstrate this a little more fully, I'm going to pull up CST Microwave Studio. So I'm going to break out of this. This is a tool that you're going to use a little bit later in lab number 2. You're going to actually play with coaxes and waveguides in lab number 2 in CST Microwave Studio. What I've done here is I built a model for a coaxial cable. So you can see I've got an inner conductor, I've got an outer conductor, inner conductor, outer conductor. These are ideal, perfect match waveguide ports that allow me to excite fields or voltages and currents on this line, and I ran the electromagnetic simulator. And so if I want to take a look, for example, at the modes in the electric fields inside the mode, you can see that I have these fields that point radially outward. But you're going to notice when I set these fields in motion, they're oscillating fields. So they point out, and then they point in, then they point out, then they point in. Right? The magnetic fields in the port are circulating around the center conductor. So my electric fields are pointed outwards, my magnetic fields are rotating around. This is actually what we expect from electrostatics and magnetostatics if I have charging current on that inner wire. I can also look at the fields. Right, so now what we're doing is looking at the three-dimensional fields. I'm going to look at a different plane. Okay. We can actually see the wave propagating from left to right. And you'll notice these fields that point from the inner conductor to the outer conductor or vice versa. Sometimes they're pointed out, sometimes they're pointed in. And I get this propagation from left to right as the wave goes down this coaxial line. The magnetic fields are circulating around the conductor, and in this particular plane, up here they're pointed out, when down here they're pointed in, and vice versa. And again, I can see the propagation from left to right of the fields in this particular case. Okay? So that's the example of guided waves on a coaxial line. I can also have guided waves on a waveguide. This is what we're going to do starting in early April. So my structure is a box, a metal box with it's got solid walls. I've got ideal matches on the two ends. I can take a look at the port modes. So here's the electric field in the waveguide port, and I can set those fields in motion, and I see that they oscillate. Likewise, I've got magnetic fields that are in the orthogonal direction, and they're oscillating from right to left and right and left. Okay. And I can look at the fields. Okay. And I can see the wave propagating from left to right. Now you'll notice something here. Right? I just froze it. Here the fields are pointed from bottom to top, and here the fields are pointed from top to bottom, and then here the fields are pointed from bottom to top. Right? And if I were to plot the field intensity, say, along the center axis, I'd have a maximum, then a null, then a minimum, then a null. And so I have a sinusoidal wave propagating along the line. That's the electric field. The magnetic field is orthogonal to that electric field, so you can see sometimes it's pointed into the board, sometimes it's pointed out of the board, again propagating down the line. And all of that is supported by a surface current. And you see there's the surface current. Now, of course, we know how the surface current and the magnetic field is related. Right? So we saw already that the magnetic field in a given plane in the center here was pointed, say, to the right or to the left. If I take the surface normal crossing the field, that's going to give rise to current flowing on the top and bottom conductors as well as the sidewalls. And I can see those currents propagating along the structure as we go. So these are the types of things that we're going to be looking at in laboratory number 2. So by way of finishing up, the tutorial question for this lecture is very short. This lecture is really just a conceptual lecture so you can understand where the wave equation comes from and what it is. We're actually not going to work extensively with the wave equation for the rest of the semester. In the next lecture, we're going to make yet another simplification. We're going to force our field to be time harmonic, and that's going to give us the Helmholtz equation. And the Helmholtz equation is the equation that we're going to apply for the rest of the semester for plane waves, transmission lines, waveguides, and antennas in the rest of this course. But there is a tutorial problem for lecture 4C that relates, it has you look at the nature of the solutions to the wave equation, trying to determine if a given type of function is in fact a solution to the wave equation.